Welcome everyone for this quick session today about unifying stream processing with fast data store. My name is Fawaz Ghali. I'm lead developer advocate at Hazelcast. I lead DevRel. And joining me today, Michael Goldberg from BNY Mellon to give you some kind of real-time use case about using Hazelcast. So what I wanted from this session is basically to answer two questions. So first question is, how far are you in this journey? The fact is that you're attending this talk or you're at this event, you probably work with streaming data or stream processing. And the fact is, some of you are using some kind of data streaming and stream processing, so where are you on this journey, right? So this hopefully can give you some ideas of how you can take your application and basically take it to next level. So looking at it is basically looking at the value of what your application does at this moment. So on one aspect is how you want to move from batch into stream processing. And on the second level is how you move from delayed action to instant action, which is what real-time stream processing is all about. Obviously, when it comes to developing real-time solutions, you need to look out for how easy it is or how simple it is to develop these solutions. So for those who don't know Hazelcast is a real-time data platform which allows you to combine stream processing and fast data store in one platform. So the cool thing about it is how easy it is to develop this solution. And obviously, if you work with stream processing, you know how hard it is. And you want to make sure your solution not only has a good performance, but also how easy or how simple to develop and maintain. So from one side, Hazelcast allows you to ingest data from multiple sources. It depends where your data is coming from. We're today at Kafka event, so you can ingest your data from Kafka and many other sources. And once you ingest this data, you have two options here. So you can do stream processing in real time, but also you can connect a historical data or batch data and load it into the platform. And obviously, you can do this with multiple clients and through multiple languages. So the question becomes here, how can you achieve this in a very simplified approach, right? So this is what we're looking at today. We're looking at developing a real-time solution in the most effective way and how simple it is. So Michael is going to talk us about a use case today, and he's going to explain how you can achieve stream processing in a simplified approach. Obviously, there are some best practices for this approach, so make sure to basically take some notes. And we are at booth 209 if you still have any question, so feel free to grab us after this session. So with that being said, I will hand it over to Mike.
Thank you. Can you guys hear me? Okay. So this is a little bit about me, Mike Goldberg. I spent my entire career developing software at various financial institutions. So I'm passionate about lean and agile software development. So I spend a lot of time practicing it and coaching development teams. So we'll try to do the same here. So our use case, about 6 years ago now, we were asked to build a system that orchestrates the work of many financial professionals across many groups, with many events happening in real time. And the system was built gradually, and the streaming features were added later as the needs of the software evolved. So today, we'll talk about a few use cases that we experienced as we were developing the software. And one of them is duplicate message detection. Second point, or second use case, is data accumulation and transformation aggregation. So this is pretty complex when you have to build it yourselves, and we used Hazelcast to solve this problem. Event correlation with delayed publication is the third use case. And the fourth one is the business transaction based on triggers, when multiple triggers happen and you have to do something when multiple events take place. So those kind of activities are pretty hard to do manually, and with the use of Hazelcast, we're able to solve those problems in a very straightforward and simple way. So let's look at the first one. Before we start looking at the use cases, Just to give you an example of how easy it is to integrate Hazelcast with Kafka, start orchestrating Kafka source into the Hazelcast platform. So we use pipelines. So in front of us is the sample code of how to configure the pipeline to use Kafka as a source. As you can see here, in the read from statement, you simply define the properties like what you would normally do when you define Kafka consumer. So these are classic Kafka consumer properties. You provide them to the read from statement, and you supply the offset and a couple of topics to read from, as many as you need to, and voila, you can start streaming the data from Kafka straight into Hazelcast platform. So the first use case is the duplicate message detection. So on the surface, it's a pretty simple problem. But what happens when you have a data flying into the system in real time and you cannot afford processing the duplicate messages? So if the requirement is that you have to process the message only once, and Kafka does not provide this capability out of the box. So you have message stream coming in, and your goal is to stop or do something when you receive a duplicate message. So in front of you is a solution that we put in place, which is quite straightforward. So we have, in this example, I show you a couple of pipelines that read the data from Kafka, and these pipelines write the data into the Hazelcast map. So once the data is written to the map, then the question is, what do you do with it? And we have a listener attached to the map that does the rest. So an example of the listener is here. So we implement a couple of interfaces, entry edit entry processor and entry updated listener. Sorry, not the entry processor, the listener. So entry edit is your happy case scenario, happy path scenario. That's when you process a new message. But when the message received writes into the map with a key that's already in the map, an entry updated event is fired, and that's where you can do different kind of processing, alert the system, or simply reject the message if you don't want to process it again. So with this approach, the duplicate detection becomes a very simple exercise with a simple listener piece of code that is in front of you. Second use case is a little more complex. So imagine if we need to accumulate the data from multiple Kafka sources and present it in a form of readable data sets, let's say through SQL or something like that. So in this case, we use the same jet pipelines, where those pipelines read the data from Kafka sources, consume them directly, and write them into the set of maps. And in this case, I show that a couple of sources could write to the same map, or each source could write to its own map. It doesn't matter. But then, after these data is written to the maps, you can expose this data as a traditional SQL source. So you can read the data like you'd normally do using JDBC interface. So the key here is transformations. So if the requirement is to transform the data on the fly, then what you can do, you can define your pipelines with various operations that Hazelcast provides, such as filtering, mapping, hash joining, merges, and so on. So there's a rich set of APIs available on the pipeline side that allows you to perform fairly complex transformations on the data as it comes in. So then when you write it to the maps, it's already transformed, and you can read it as a traditional source. The third use case is when you have to correlate multiple events, and if the requirement is to publish the data to Kafka when certain set of events took place. So in this case, I show here in the diagram internal events, but they don't have to be internal. They could come from anywhere. The goal is to accumulate a set of events, and when certain events are correlated, only then perform certain operation, let's say publishing a message to a Kafka topic. So in this case, we have to write, sorry, let me step back, click too early. So in this case, we have to write the events into the map, attach a listener to the map that listens on every event written on an entry, and when this event results in the requirement to publish something to the Kafka, only then we put this entry into another map with an expiration. So the trick here is that you can put the logic in the listener to tell the entry when the event should be published. And the way it's done is through the expiration. So in this case, the pipeline would listen on a distributed map, and only when the entry is expired from the map, the message will be sent to Kafka. And again, I'm showing this as an example because it's very simple to do in Hazelcast. All you have to do is provide a time to live interval on an entry that you're placing into a map, and the pipeline itself will read through the journal and publish to Kafka very easily. The third one is probably the most complex in these examples, is when you have to have a business transaction performed based on the multiple triggers firing or multiple events happening, and you have to perform a business transaction when certain events occur and you need to correlate between them. So in this case, the jet pipelines write to the map. We attach the interceptor to the map, and I'll show you an example of this interceptor. This interceptor mutates the entries and writes to the map mutated objects. A listener attached to the map that then determines when the data should be published and publishes, in this case, I put as an example to Hazelcast queue, and you have an external service listening on that queue that performs complex business transaction. So here's an example of the interceptor. You have an intercept put operation that allows you to receive both old and the new entry from the map. The new is being written, the old one, that's the one that already exists in the map. You compare them, you can evaluate both objects, and depending on the rules, you can update the properties. But once those properties are written back to the map, the listener can then perform an operation where the entry, let's say, is evicted if you use the eviction-based model. The idea is that, and the example here shows how easy it is to take an entry from a map, put it on an internal queue. In this case, literally a couple of lines of code. And you have an external listener listening on the queue that can take this data and process it forward. So a couple of words about the metrics. So we're able to achieve sub-millisecond, in some cases, processing times on those messages that we process. So it's extremely fast, and the nice thing about this setup that it allows you to grow with your data. So you can scale horizontally quite easily by adding new nodes of the Hazelcast cluster, almost in real time, so you don't need to do anything special. You can just bring up additional nodes, and it allows you to parallelize the processing very gently. Hazelcast operates in memory, no I/O, which makes it very fast. And it operates in a lock-free mode. And that's another big advantage of using the approaches like this, because you don't need to worry about locking your entries like you would do with the traditional tables. You can safely operate on the data as it comes in. The way it's done is by introducing partitions into the Hazelcast. So each entry is processed on a specific partition. And there's a concept of the processing thread that operates on those partitions. So the guarantee is that every partition is processed by a single thread. So as a result, you don't need to lock your entries when you perform parallel processing. It's done natively by Hazelcast. Few recommendations or key takeaways. First, keep it simple. That's an important consideration because as your system grows and becomes more complex, it's easy to slow down the Hazelcast cluster when it consumes or when it publishes the data. So keeping it simple is important. Avoid costly operations. So when you perform complex data transactions or transformations, it's better to use job executors or listeners that are offloaded from the partition threads, so you don't slow down the processing of the main flow. Leverage Kafka and pipelines and Hazelcast events for efficient problem solving. Bringing those technologies together allows fairly sophisticated operations to be performed on the data without spending too much time coding them. Another recommendation is to keep an eye on the memory utilization. As you process thousands, sometimes hundreds of thousands of transactions, you may see the memory spiking and the garbage collector may start getting overwhelmed. So you need to watch for these events and size the cluster accordingly. So very often, having more nodes with a small amount of heap on it gives you better performance than running small number of large nodes. And the last thing about resiliency, so Hazelcast has plenty of features to configure resiliency to make your system very resilient with very high uptime. So you need to choose what features you want to use and how to configure it, but Hazelcast provides many of them out of the box. So you have to configure your Hazelcast cluster for resiliency requirements that your system has, obviously. And back to you.
So,
thank you.
Yeah, I mean, the goal or the main thing that you want to focus on when it comes to stream processing is First of all, you need to think about your use case, right? This is by far the most important and crucial part. It's nice to hear about technologies and what they do for stream processing, but the question always comes back to your use case. So for that reason, what I would advise you to do is just come grab me afterwards, or grab Mike, or stop by our booth 209 just to discuss your use case in more details. And what I wanted here is to describe how easy it becomes to handle and process data coming from Kafka. So I wanted to go back to this and give you some idea on 3 different things that you need to look for when it comes to stream processing. So first of all, stream processing means you need to process data before you store it into database, right? So what we want is not to ingest data, store it into database, load it back, and process it. What we wanted is just to make sure that we were able to do it in this very moment. And this is crucial, right? Because the game here is to minimize latency. And when it comes to minimizing latency, right, we're not talking about the real-time data only, right? Because that's just part of the story. The full story is combination between real-time data and historical data. You always need historical data for your real-time application. There is no way to benefit from only real-time data. Real-time data gives you insight what's going on with this, collection, but you still need to provide context into it. So that's the first part. Second part is how you can load your batch data or provide contextual value into your application. And remember, right, so if you are a developer, for example, or you're a solution architect, or even if you're working in machine learning, the goal here is to use as minimum tools as possible, right? So instead of having 2 or more tools to provide the same solution, you need basically to think about the time to learn this tool, but also to minimize number of tools, because this will save you lots of time and effort afterwards when it comes to maintaining this solution. And with Hezekiah, you don't need to learn new language. You can connect any client. So Hezekiah is built on the Java virtual machine, so you can connect it to Java client, but also you can use Python, for example, or C#, C++, or C#, or even if you're not a programmer, if you want just a quick solution, we have a very rich SQL interface. So if you're coming from data science background, you can run SQL on top of Hezekiah. Obviously, you can also output results if you're working, for example, for machine learning. Hezekiah is the ideal solution for serving this model. But to go back again to the point where the use case. So what I wanted from Mike is, especially because any talk you go to, it's nice to hear about technologies. So also it's nice to see how it works in real life scenario. So can you just give us a little bit of best practices for someone who is new to stream processing? What advice would you give for someone who wants to get started with stream processing?
Well, the first advice would be to start slow and start simple. Before solving complex problem, try to simplify it and see how it works. And try to build up on this experience. It's always easier to solve a problem quickly and see the result before adding complexity on top of it. So going in short steps and getting the feedback right away about what you just did makes it easier to move forward. Then you look back and realize, wow, I built a complex system, but you did it in short and simple steps. So don't try to boil the ocean and solve all the problems all at once. Go easy. Another thing is that if your requirement is performance, try to set your performance goals in the form of tests at the beginning. It's much easier to stop when you made a change and realize that your change is causing the performance than to build the entire system and then try to test and realize that it doesn't perform. Then you have to redesign everything. So if you build your test goals up front and then start building the solutions while running your tests and validating that your solution still performs, you're more likely to build a good result with performance in mind. So that would be my couple of recommendations.
Thanks, Mike. So quick notes here. So we have a very large community online. So I would encourage you to join this community. Feel free to scan this code to join our community Slack, so where you can get access to our engineers. or even our solution architects, or even if you want to describe your use case or even contribute to our source code. We're running a happy hour tomorrow, so make sure also to join this, scan this code. I think you got flyer as well. So we got some few seconds for one or two quick questions. So any questions here? Thank you.